when we talk about limit of a function, so what do we mean by this? Suppose we have a function fx is equal to 2x, right? And we want to evaluate limit x tending to 1 f of x. Now for this, the meaning of limit is if you are approaching to 1 from both the sides, that is from left as well as right. Now what do we mean by approaching to 1 from left as well as right? The meaning is if you are moving to 1 from values bigger than 1 and if you are moving to 1 from values smaller than 1. And we see that to what value the function is approaching. And if we observe that while approaching to 1 from both the sides, the value of the function also approaches to same value. Then we say that limit x tending to 1 fx exists. Now for example, suppose you have x here and you have fx here. Here suppose we write 1. Right? Now approaching to 1 from here, this means let's take 1.2 here and 1.1 here. Here let's take 0.9 and here let's take 0.8. So what is the value of function when x is 0.8? It's 1.6. What is the value of function when x is 0.8? It's 1.8. Here it's 2. Here it's 2.2. Here it's 2.4. So what we observe in this case is when you are approaching to 1, the value of the function is approaching to 2. See, here it's 1.6, then near to 2 and then here it's 2. In the same manner from right hand side. So this approaching from right and left is said to be finding right hand limit and left hand limit. Right? And the notations are limit x tending to 2 minus fx. This is the notation for left hand limit. And this is limit x tending to 2 plus fx. And this is the notation for right hand limit. And like in this case, we observe that from both the sides the function is approaching to same value. Right? So we say that for fx is equal to 2x, limit x tending to 1 fx exists. And what is the value of the limit? It's 2. The value of the limit is 2. Right? So we have this thing over here. Now, so using this, we say that when we can say that the limit of the function will exist. So limit x tending to a fx exists if and only if limit x tending to a minus fx is equal to limit x tending to a plus fx. Right? So now this is if and only if statement, means this is a both way statement. If limit x tending to a fx exists, then right hand limit and left hand limit will be equal. And if the right hand limit and left hand limit of a function are equal, then we can say that limit x tending to a fx exists. So you can use this statement both ways. If this is given, these two will be equal. If these two are equal, then this is true. Is it right? Right? Now, the next thing which we have is, now what we will observe is in case of polynomial functions, in case of polynomials, we will observe that when you approach to some value of x from left as well as right, the value of the function approaches to the same value which is the value of function at that point. Like we observed in the previous example. The value of fx at x is equal to 1 is what? 2. And we observed that when we were approaching to 1 from both the sides, the function was also approaching to 2. Right? So this is true only in case of polynomial function. So when we evaluate limit in case of polynomials, you just simply have to substitute that particular value. Right? Now can you tell me in which cases we will find left hand limit and right hand limit separately? Here we have not evaluated the left hand limit and right hand limit. We said okay, we will substitute the value. Like if I say limit x tending to 2x square, what will be the answer? It's 4. Right? Is it or not? So we get limit x tending to 2x square is equal to 4. So after this, what we have over here is, so this is how we evaluate the limit of a polynomial function. Right? Now the next thing which we have is algebra of, next is algebra of limits. Here you have limit x tending to a fx plus gx. Means when you have the function in the form of sum of two functions. So in this case it is same as limit x tending to a fx plus limit x tending to a dx. Means we can find the limit of each function separately. Right? This follows for subtraction also. Right? The same follows for subtraction also. If you have limit x tending to a fx minus dx, the same result will follow. Limit x tending to a fx minus limit x tending to a gx. Then what you have is, if you have limit x tending to a fx into gx, the same result will follow. Limit x tending to a fx into limit x tending to a gx. Right? And the same goes for division also. Limit x tending to a fx upon gx, right, is equal to limit x tending to a fx upon limit x tending to a gx. Is there any condition required here? No. Any condition required here? Yes. Limit x tending to a dx should not be equal to 0. Right? This condition must hold over. Is it okay? And one more property over here is, that is limit x tending to a alpha into fx, where alpha is any scalar. Scalar means any real number. Right? So this can be evaluated as alpha times limit x tending to a fx. So if you have any constant multiplied with the function, you can take that constant out of the limit and evaluate the limit of the given function. So this is the algebra of limits. Right? Now let's evaluate few limits here. Calculate this limit x tending to 5 x square plus 2x plus 1. This is
26.
5 square plus 2 into 5 plus 1. So this is 25 plus 10 plus 1. So this is the limit in case of this function. Now if you have limit x tending to 2 x square minus 4 upon x minus 2. Now in this case, if you will substitute 2 in place of x, what we observe is this is 2 plus square minus 4 upon 2 minus 2. Right? What do we have? We get 0 by 0. Right? Which is indeterminate form. This is indeterminate form. So in such cases, you have to convert the function to the normal form. You can't evaluate the limit in such cases where it's indeterminate form. So 0 by 0 is indeterminate form. So we have different ways for doing this. One is by factorization. Second is using rationalization. And the third is maybe using a special formula. But that formula is applicable only for a specific form of the function. Right? So we can have factorization, we can have rationalization, we can use the special form, and one more thing, there could be a possibility where we will use substitution also. By changing the variable, we will convert the function from indeterminate form to the normal. Right? So the very first is when we have to using factorization, like this case would be. So what you have is limit x tending to 2. What can you write x square minus 4 as? X plus 2 into x minus 2 upon x minus 2. This gets cancelled. So the factor which was creating trouble was x minus 2. We have removed this from numerator as well as denominator. So what is the answer? 4. So this is factorization. Let's take one more example. Suppose you have limit x tending to 1, right? X square minus 2x plus 1 upon x square minus 1. What we will have over here? Is it of the form 0 by 0?
Yes.
Yes, you put 1 in place of x, what do we get? We get numerator 0 as well as denominator 0. So you write it's again 0 by 0. So it's limit x tending to 1. You can write this as x minus 1 whole square. This is x plus 1 into x minus 1. This gets cancelled. What do we have? Answer is
0 by 2.
1 minus 1 upon 1 plus 1. So 0 by 2, that is 0. So this is how you can evaluate the limit. You can convert the indeterminate form to the normal form where we can evaluate the limit easily. Right? This is how we use factorization. Now come to the next type, that is where we use rationalization. Now for rationalization, it's not necessary that we will rationalize only the denominator, like in that case, factorization. In the first example, we had to factorize only the numerator. In the second one, we had factorized numerator as well as denominator. There could be a possibility where we will be factorizing only the denominator. So it depends on the given function. In the same way, for rationalization, the same thing follows. You may have to rationalize numerator only, you may have to rationalize denominator only, and in some cases, you will be rationalizing both numerator as well as denominator. Like, let's do this one. Limit x tending to 0, root 1 plus x minus root 1 minus x upon x. Which form is this? Is it 0 by 0?
Yes.
It is. You put 0 in place of x. What you will have? Root 1 minus root 1. That is 1 minus 1, 0. And you have put 0 in place of x. It's again 0 by 0. That is indeterminate form. Right? So, here, if you look at the function, you can't factorize this. Right? So, we will have to look for some other approach. And here we will use rationalization. So, it is root 1 plus x minus root 1 minus x into root 1 plus x plus root upon x. So this gives me limit x tending to 0 it's root 1 plus x plus root 1 minus x. So let's complete this. This is 1 plus x minus 1 minus x upon x into root 1 plus x plus root 1 minus x. So what do we have in the numerator? Limit x tending to 0, we get 2x upon x into root 1 plus x plus root 1 minus x. This x gets cancelled. And we had problem with x only. Right? This was only giving us the 0 by 0 before. So, what is the final answer? Now put 0 in place of x. The answer is 2 by 2. This is how we use rationalization for evaluating the limit of algebraic function. Right? Now, the next is the special form where you have for that the formula is limit x tending to a x to the power n minus a to the power n upon x minus a. You will not apply this formula unless until the function is given in the same form. Right? It's x to the power n minus a to the power n upon x minus a. This is equal to n into a to the power n minus. Right? Like in the very first example where we had limit x tending to 2x square minus 4 upon x minus 4. It was not difficult to factorize x square minus 4. We had factorized it easily by writing it as x minus 2 into x plus 2. But if the power of x is a big number, so at times it's not easy to factorize. So we go with this special result. Right? Like suppose you have limit x tending to 2 x to the power 5 minus 32 upon x minus 2. Right? Compare it with the above result. Is the function in the same form?
Yes.
Right? Yes, it is. Yes, you can write it as limit x tending to 2 x 2 to the power 5 upon x minus 2. So x to the power n minus a to the power n upon x minus 2. Right? So this is 5 into 2 to the power 5 minus. Right? So it's 5 into 16. So this is the third form, third way where we can change the indeterminate form to the general form for evaluating the limit. You will reduce the indeterminate form to the normal form of the function. Right? So first was factorization, second was rationalization, and the third was using the special result, which is limit x tending to x to the power n minus a to the power n upon x minus a is equal to n into a to the power n minus a. Now, let's move to the trigonometric limits when we talk about limits of trigonometric functions. So for that, what we have is for trigonometric functions. Now, like if I say evaluate limit x tending to pi by 2 cos x plus, right? So in this case also you will observe that you can simply substitute the value and evaluate the limit, right? So what will be the answer?
1.
Is it? Because cos pi by 2 is 0. So we get the answer as 1. But here also there is a possibility that we get the form 0 by 0. Right? So to avoid that, we have two standard results over here. One is limit x tending to 0 sin x upon x is 1. Right? And the other is limit x tending to 0 1 minus cos x upon x. Right? This result is C. Okay? So these are the two standard results which we will use for evaluating the limits of trigonometric functions when we are getting the indeterminate form. That is when we are getting the form of 0 by 0. So these are the two standard results which will help us. Now when the trigonometric functions will be clubbed with algebra, right? In those cases there is a possibility that we will be using this result as well as we will use factorization on the other hand. Right? Simultaneously we would be using the previous three approaches also. If you have the function as the combination of trigonometric as well as algebraic. So there is a possibility that you will use factorization as well as this standard results for evaluating the limit of given function. Is it okay? Right? So the next thing which we have is let's do some question. One more thing which you must take care of here while applying this result, like suppose you have limit x tending to 0 sin 3x upon x. Okay. So what you have over here is x limit x tending to 0 sin 3x upon x. You can't apply this result directly because right now the function is not of this form. Here you have sin x upon x and here we have sin 3x upon x. So what we do is we multiply the numerator and denominator by. See, when x is approaching to 0, x is tending to 0, 3x will also tend to 0. Right? When x is approaching to 0, 3x will also approach to 0. So what we have, take this scalar out and then limit x tending to 0 sin 3x upon 3x. So what is the answer? Because limit x tending to 0 sin 3x upon 3x will be 1. So we have used this result. So while applying this result, please make sure that the given function is exactly of this form. Because if here the angle is some multiple, if here the angle is some multiple of x, then in the denominator also we must have the same quantity. Is it okay? And please be careful while doing the question that what is the measure of this x in all the cases?
Radian.
Yes. This x, see, when we talk about trigonometric function, so these angles are always in terms of radians, right? So, if you have this question, limit x tending to 0, sine of x degree upon x, right? If we have this limit x tending to 0, sine of x degree upon x, you can't evaluate it directly because this angle is in radians. So for this, what we will have to do first? Yes, we will convert it to radians. So what can I write sine x degree as?
X by
Sine x degree is equal to how many radians? It's limit x tending to 0, sine, is it? Pi x upon 180, right? Upon x. Okay, so when I have sine of pi x upon 180, now this is in radians. So I will have to take the same quantity over here, right? And when I multiply the denominator by this, I will have to multiply the numerator also by this quantity. Now pi by 180, it is a constant, it is a scalar, right? So what we have, what will be the answer? Pi by. So this is how you need to convert the function to this specific form. And please be careful, you can't do any working when the angle is in degrees. Convert it to radians. Is it fine? Is it okay?
Yes.
Now, this is trigonometric. Let's do some more questions over here. Limit x tending to 0, one minus cos mx upon 1 minus cos mx. So suppose we have this, right? Which form is it? Again 0 by 0 indeterminate form, you put 0 in place of x. What do we have? Cos 0 is 1, so 1 minus 1 0, here also 1 minus 1 0. It's again 0 by 0, right? So this is limit x tending to 0. Now in case of trigonometric, like there we had factorization, rationalization. In case of trigonometric, one approach is using the special form, the special result. What could be the other possibility? We can use trigonometric identities, right, for evaluating the limits. Like what can we write 1 minus cos mx as? We can write it as 2 sine square mx by 2, right? And I can write this as 2 sine square nx by 2. So this 2 gets cancelled. Now this is limit x tending to 0. What can you write this as? This is nothing but sine mx by 2 whole square, right? And this is sine nx by 2 whole square. Can we apply the standard result here? Can we apply the standard result here? No, right now we can't. Right? So, for this you have limit x tending to 0 sine so it's upon mx by 2 whole square. So here also I will have, when you are multiplying denominator by some quantity, you will have to multiply numerator also with the same quantity. And in the same manner over here, it's sine of nx by 2 whole square. So it is nx by 2 whole square upon nx by 2 whole square. Right? What can we write this as? It's 1. If you apply the limit. What about this part? It's again 1. Right? And if you look at this 2 gets cancelled, this x gets cancelled. Right? And we are left with the scalars only. So the answer is whole square, right? Right? So this is how you can use trigonometric identity, you can use the standard result, right? Do this limit x tending to a sin x minus sin a upon root x minus root a. Limit x tending to a sin x minus sin a upon root x minus root a. So, in such case, what we will do is, yes, how we can start? Use the identity sin x minus sin. Right? Yes, it's limit x tending to a. It's 2 cos x plus a by 2 into sin x minus a by 2, right, upon root x minus root a. Okay. Now still we have the indeterminate because this is giving us 0 and here again this is giving us 0. Right? So how we will remove? Now you can't factorize this, but we have the possibility of rationalization over here. Right? So this is limit x tending to a 2 cos x plus a by 2 into sin x minus a by 2. It's root x plus root a upon root x minus root a into root x plus root a. So what do we have? It's limit x tending to a 2 cos x plus a by 2 into sin x minus a by 2 into root x plus root a upon. This gives us x minus a. Still we are short of some quantity, and that is we must have 2 here and we should have 2 here. Is it? So when you apply the limits, what is this resulting one? 1. Right? And rest with all the factors we don't have any problem. So this 2 gets cancelled. Right? So what is the final answer?
Cos 2a.
Cos a plus a. And here it is.
Same thing.
So we get 2 root a cos. This is the answer. Right? So here, see, this was the question where we have applied trigonometric identity as well as rationalization. So we have clubbed the 2 approaches for evaluating the limit of this. Right? Now, the next, let's do one more question. That is limit x tending to pi by 4 sin x minus cos x upon x minus pi by 4. by 4. Right? We have no identity here which will help us. Here we had used sin A minus sin B. Here we have sin minus cos upon x minus pi by 4. So another approach which we use for reducing the function from indeterminate to the normal form, that is substitution. So here we will go with substitution. So x minus pi by 4 is equal to t. Right? See, when you are substituting this, you are changing the variable. Right? Right now the whole function is in terms of x. It's a function of x. And now you are changing it in terms of t. So you will have to change the limit also. There x was approaching to pi by 4. So you will have to see to what value t will approach. So when x is approaching to pi by 4, t will approach to 0. Right? T will approach to 0. So its limit t tending to 0, sine of t plus pi by 4, right, minus cos of t plus pi by 4 upon, is it? So you have limit t tending to 0, open it, using sin A plus B, which is sin A cos B, so that is 1 by root 2 plus cos A sin B, so sin pi by 4, it's again 1 by root 2, right, minus cos A cos B minus sin A sin B, which is again 1 by 2. Open the brackets, see what do we get? It's limit t tending to 0. What do we have here?
2 sine.
Yes, it's 2 sin t into 1 by root 2 upon. Now when you apply the limits, this will be 1. Limit t tending to 0 sin t upon t is 1. Right? So what we have? Final answer is root. Okay. So this is how we use substitution, right, for evaluating the or reducing the indeterminate form. Now let's do some more questions. The next which you can have is limit x tending to 0, limit x tending to 0, 1 minus cos 2x upon x square. Yes, how it will start?
Cos 2x.
It's again, is it 0 by 0?
Yes, sir.
Yes, it is, right? So, what you can follow over here? What can I write 1 minus cos 2x as?
2 sin
You can write it as 2 sin square x upon x, right? So, what is the final answer?
2 by
What can you write this? This is nothing but sin x upon x whole square, right? So when you apply the limit, this is 1. So what is the final answer?
2.
It's 2. Right? Write down the next. Limit x tending to 0. Limit x tending to 0. 2 sin x minus sin 2x upon x cube. 2 sin x minus sin 2x upon x cube.
We will take 2 sin x cos x common.
So
2 sin x
here
common from
it's 2 sin x. What can you write sin 2x as?
2 sin x
2 sin x cos x. Right. 2 sin x cos x upon x cube. Right. Take
2 sin x
2 sin x common. Right. Let's limit x tending to 0. Take 2 sin x common. What are we left with?
1
1
minus cos x.
minus cos x.
Now write x cube as x into x square. Now sin
Upon
x into
x cube. Then still it is of the form 0 by 0, right? So what you have over here is limit x tending to 0, 2 sin x. Write this as, what can I write 1 minus cos x as? 2 sin square 2 sin square x by 3 upon x cube. So write x into x square. So you have sin square x by 2 in the numerator. So we need x square by 4 in the denominator. Is it? So dividing by 4 and multiplying by 4. So if you look at what is this part equal to? 1. What is this part equal to? Again 1. And what are we left with? It's 4 by 4. This is how we evaluate the case of algebra, right? And rectangle, right? So for this, we have discussed all the approaches: factorization, rationalization, using the special form, right? And the functions which were in the form of combination of two, trigonometric as well as algebra, right? So be careful. The first step here, put the values, and after that see if it is in determinate form, then only we go with the